So for the final presentation today, we've got Associate Professor Stefan Maier. So he works quite a lot on remote sensing and fire, and he's actually responsible for, as you heard Andrew speak earlier, about the burnt area mapping. He does a lot of that with MODIS, so a lot of this really broad scale burnt area mapping that's really important and underpins a lot of management decisions that are made. So he's going to talk about a little bit more of the technicalities of what he does in terms of creating some of the maps and some techniques that he uses for that.
Hello everyone. All right, last one. So I'm going to talk, well, we heard a lot about fire mapping so far, and Andrew has shown you a map that has been created before we used remote sensing to look at where fires are. And I've got a map of the whole of Australia here, which is derived from remote sensing, the fire frequency. And as Andrew alluded already, it is quite different from what people thought it would be. Just some interesting statistics. In Australia, every year between 300 and 700,000 square kilometers burn, so every year. And that's, I just put that as an example here. That's between 1 and 2 times the size of Germany. So it's a huge area. But having heard the previous speakers, you might think, yeah, well, fire and remote sensing, that's basically a solved problem. It's operational now, we just do it on a regular basis. But the thing is, fire is not fire. And I've just got 2 examples here. So you might have a fire like the one at the bottom left, which is very low intensity, just affecting the understory. And the result on the vegetation, you can see on the top left, we've got quite large patches that stay unburned. And that's quite important from an ecological point of view, because these are places where animals and plants can retreat and then repopulate the burned areas. Or you can have a fire like this one at the top right, which basically kills a lot of the trees. And if you've got repeated fires like that, there won't be any tree left. And you can sort of see an indication of that in the bottom right picture. So, well, what does that mean? Well, burnt area mapping, just knowing where fire was, isn't really enough. We need to know a bit more about the impact on the vegetation, and that is what we call patchiness. So we want to know whether a fire has burned a plot completely or whether it was quite patchy and left some bits unburned. Well, a bit more on patchiness. Another part of Sophia's work was to look at patchiness on the ground here in the tropical savannas. And she found that unburned patches, the majority of the unburned patches are smaller than 5 meters. So quite small bits. And now a question for the students, because you all looked at the different characteristics of different sensors. Based on that information, what sensor would you use to map this patchiness? So you want to pick up things that are in the order of 5 meters or less. Yeah, so for example, worldview. Yeah. Problem is we want to do this for the whole of Australia. Worldview is a commercial sensor, quite expensive. For the whole of Australia, we can't afford to do that. But even Landsat, what's the pixel size of Landsat? We try to find things that are 5 meters in size or less than that. But even if we would have a huge budget, we still couldn't do it because of this. So the left image is just after the fire. The right-hand image is 10 days after the fire. And we can see quite a lot has changed already. A lot of the ash has disappeared, and we've got leaves lying on the ground. And how fast this happens totally depends on the environmental conditions. And that makes it hard to actually detect these changes. Just another example here. A lot more leaves in that case. And if we look very closely, you can see some resprouting. The grass is regrowing after 10 days after the fire already. And with these high-resolution sensors, we just can't get the imagery often enough. to do that kind of work. So what's the solution? Well, if you look at a patch on the ground, let's say it's patchy like that, and the area represents a pixel of our sensor, of our coarse resolution sensor, what the sensor sees is a mixture of that, of these different components on the ground. So in this case, like a darkish green. And what we do is we apply something what we call unmixing. And in this case, it's a linear unmixing method. So we try to estimate how much of that pixel, what percentage of that pixel got burned, and what percentage didn't get burned. And I don't want to go into the details. It's called linear unmixing. I think, yeah, would take up too much time here. And here's just an example. So we've got a reasonably large fire, but not unusual in northern Australia. So if you look at the scale, it's quite a big fire. And what we can see is that there's quite some variability in this patchiness. So we've got areas that burned completely. There was nothing left on the ground. And other areas that just slightly got affected by fire. And these are obviously areas where we've got less of an ecological impact through the fire. Here's another example. This is from the automatic burned area mapping using MODIS that Andrew mentioned. The different colors here represent different days of where the fire was. So this fire burned over, I think, almost 2 months. And it started somewhere in here and then moved in various directions. You can see the progression of the fire here. Probably should use the mouse for that. So from here it moved towards the east. And you can see on some days it made just little progress, and on other days it made quite big progress, like here, for example. What you can also see in that automatic mapping, where we've got an updated map every day, is that the fire, whoops, try to get that to work, moved that way, and it stopped here. And that's a creek. That creek really stopped the fire. But what we can also see further on, the fire jumped the creek further up, where the creek probably wasn't as wide, and then moved into that area this way. If you do mapping just a few times a year, you can't see these differences. You only get the total map. All right, so for the same area, for the same fire, we've got here the patchiness information. And again, you can see quite a lot of variability. In general, some of the areas where the fire moved very fast and was quite intense, there was very little patchiness, so it completely burned the area. Some other areas, we can see an area that burned during one day. Some bits are burned with little patchiness, so very completely. Others with a lot of patchiness. And the difference between the two areas is that one part burned during the day, high temperatures, usually more wind, low relative humidity, and other areas burned during the night. Lower temperature usually means higher humidity, relative humidity, and that just keeps the fires small, and therefore they patch the area, they burn the area quite patchy. Looking at it from a different angle, just as a reminder, we live here in a wet, dry season climate. So we've got a few months with a lot of rain, and then a few months with basically a drought. But what changes during that time are temperatures. So early in the dry season, we've got relatively low temperatures, like now. Later in the dry season and in the build-up, we get quite high temperatures, especially during the day. And if we now, for a certain area, and in this case it's parts of the top end, if we now look at the values that we pick up with that algorithm in terms of patchiness, you can see quite a bit of a distribution. So on the average is probably just below 50% of a MODIS pixel that we detected as burned really got burned. There are very little areas that got burned completely. And if we now progress through the year, we can see how that maximum is shifting to more complete burns. And then what we can see later in the dry season, we can start to see another peak appearing. Bad timing. So we start to see two peaks. We can see a peak with less patchiness, with more complete burns, and a peak with less complete burns. And the more complete burns are due to the fires that burn during the day, and the less complete burns are happening during the night. And I think that's it. Yeah, I won't go to the validation. So the question was whether I will look into how these different fires that I can now pick up with remote sensing have got different impacts on ecological impacts in different vegetation types. I'm a remote sensor. I'll leave that to the ecologist. So this is actually a very rich data set, and it's a big step forward. Like in the past, where we didn't have any burned area maps, and we had some thought about what's happening in the landscape, to having burned area maps, which look completely different and totally changed our understanding of the landscape. And now we've got more detailed information about the type of fire. So that's, again, another step forward. So we've got now 15 years of data for the whole of Australia. Yeah, so this eventually will go into NAFI and will be made available to fire managers, because they're obviously interested in that as well. And it will eventually also feed into greenhouse gas emission estimates, because from an emissions point of view, that obviously makes a difference whether you've got an understory burn that's very patchy or whether you've got a complete burn that takes out half of the trees. Not yet, no. I wanted to look at that, because the emissions calculations at the moment, they use fixed values, one for the early dry season and one for the late dry season. But as you can see there, even within one fire, there's quite some variability. And we'll have a look at what the impacts are.